allows us a linear equation with a slope equal to negative k. Now k is always going to be positive, so negative k is going to make a negative slope. Okay? And so if we plotted this thing versus time, that's on the y-axis, that's on the x-axis, that would give us some information about the rate of this reaction. And that looks like this. I'll just go ahead and uncover the rest of it. K represents the slope, well, negative k represents the slope of the line. And the y-intercept would be whatever the initial concentration, natural log of it, of the reactant was. That I want you to write down. And this part in red, that's why I changed color. This is important. Put a box around it, put a star next to it, something to make it obvious. These bullet points. Now N2O5 was specific to that reaction, that example we were talking about. Normally I'm just going to have A represent the reactants and then whatever for the products, but you'll see in the next couple it's just going to be an A. So you just know this is the reactants. So the ln of the reactant concentration is plotted versus time. Initial concentration is the y-intercept. Yes. Write the equation up here too. You don't have to call it y and x, but just that. That is the standard form. I mean, the N2O5 is, again, specific to that example, but this is the general form of a first order integrated rate law. Question, man? Not much. We don't do much at all here.
That's like.
You go on though and study chemistry. You do lots of calculus. Yep. We good on this slide? Put a box around that or highlight it.
I'm still trying to figure out how 1 over concentration of N2O5 is equal to ln of something.
Oh, it's just like
okay.
It's calculus.
Now this slide is about the K value. The rate constant K is a very big deal because it's the rate constant that really gives a snapshot of how fast the reaction is going. K does change with temperature, but just know that the bigger the K value, the faster the reaction goes. And remember, K represents the slope, so the steeper the slope of those graphs, the faster the reactions are. Yeah?
Why do they always put these graphs? Like, we had K last chapter.
Yes, we did, I know.
It just confuses me.
Yeah, by the end of this chapter, and then we'll start next chapter on equilibrium that has K's all over the place.
K for constant.
Yeah.
K when stand.
Yes, I know.
Why don't we just
Wait, so
I know. Yeah.
wait, so aren't there like 3 different K's now that we have to worry
Oh,
about?
also potassium.
Oh yeah, 4.
I hate it.
Yep. The rate constant is going to be a lowercase k. The equilibrium constant is a capital K. At least you have
And then
that.
with Kelvin's.
And then there's Kelvin. Yep. Yep.
One is like slanted.
Yeah, I know. It is.
Yep.
Why not use?
So you will always have to determine the K value when you do these exercises. You're going to see soon. And make sure that you always put the units on your K. And the units are not always the same for K because the order of it is going to dictate what the units are.
Fun.
It's a little bit frustrating. I love teaching this chapter, but it's frustrating at the same time because there's so much that I need you to know in order to understand everything. We just can't do everything all at once. So you're kind of left hanging like, okay, what really do those orders mean? And how do you find them? Well, we don't know yet, but we will. That'll be good. You good with that? I want to show you this example. We're going to come back to it later on this hour, but take a look at this as an example problem. We're not going to do anything with it yet. Okay, so just take a look at this. The decomposition of hydrogen peroxide was studied. So there's only one reactant here, so let's talk about the rate law with respect to that. This is concentration of H2O2. It started at 1 molarity at the beginning, at time 0. And then, as the reaction proceeds, the amount of the reactant goes down because the amount of products are going up. So this constantly goes down. I shouldn't say constantly goes. It goes down every time. We don't know how much or by how much. And then over time. So down here it says, they're defining the rate as the change in hydrogen peroxide over time. Determine the rate law, comma, the integrated rate law, comma, and then the value of the rate constant. Now, what's the difference between the rate law and the integrated rate law? When they don't say what kind, they mean the differential rate law. We haven't learned how to find that yet. But we will. We can't find the integrated rate law. What we have to do, though, is we have to take this data and take the natural log of these, plot that on a graph versus time. If that gives you a straight line, that means it's a first order. And you can write the rate law out for it. It's very similar to that N205 example that we did. However, if you plot natural log of this concentration versus time and it doesn't give you a straight line, that means that you've used all that time to find out that it's not a first order. Now you got to figure out whether it's 0 or second order.
Oh my god.
So I can't say that you've wasted your time, but you kind of have. Because now you know that it's not first order, but you haven't answered the question either. You got to figure out which one it is. These are fun. Fun for me
I
at
like
least.
them already. So wait,
I think my life
Yeah.
is used
Yeah,
for
it's like-
something actually.
so they asked us to find the rate law and the integrated law for rate law?
Yes.
But that's like still the same thing because like concentration over per unit or.
The concentration versus time data gives you the integrated rate law, but from the integrated you can figure out what the differential rate law is. But we haven't learned about that yet, so yeah,
Mind blown.
can't do that yet.
Solve.
But we will, and the normal rate law is pretty simple. I will tell you that most of this chapter is pretty simple once you have enough knowledge of it. At first it looks like, man, it's so disjointed and I really don't know where we're going. But as you kind of see it develop, it becomes, you say, man, I wish every chapter could be like this. You will. Okay, so anyway, to know if it's first order, then you have to take the natural log of the concentration versus time, plot. If it's a straight line, then it's first order. If it's not first order. You got to do something else. And we'll talk about that, what that something else is. The problem also did ask you to find what the concentration would be at 4,000 seconds. We're not going to worry about that.
What?
Don't write that down.
You should have said that.
Wait, don't write this down?
No, on the previous slide. I thought I already did say that.
Yeah, you did. It's just, yeah, I thought that you were saying it again for this.
Oh, yeah, no, this
video
part.
proof.
Okay, now this is going to be, we're going to assume that this A yields B is a second order reaction. Yes. I'll tell you what to write down. Because I'm going to derive this one too. And you don't have to see this. Okay, so if it's second order, remember what that means. That means if I double the concentration of A, the rate's going to go up by 4 times. If I triple it, the rate goes up by 9 times. That's what second order means. So that means that the change in A over time is going to be equal to K times concentration of A squared. That squared there means it's second order. Okay?
Yeah.
Let's do another differential equation for you.
Wait, did we write this down?
Nah, you don't have to. You don't have to. So let's move on now. I'm going to change those deltas to D's. Because mathematicians like to do that. I'm going to move that negative dt over again with the k, so it's going to look like this. Negative k dt equals, that a squared is going to go over there, 1 over a squared dA. Vinny, does that suit your approval?
I love it. Totally.
Okay, so same thing. Let's take the integral from some interval 0 to t, and what are we going to get over here? Looks like the same thing, isn't it? Negative kt.
Yeah.
Over here, what is the integral of 1 over a squared dA? Yes, ma'am?
Negative 1 over the concentration value.
Now, that's got to be over an interval from 0 to t. So it's going to be a at some time t minus negative 1 over concentration at a at time 0. Yeah?
Yeah, man. Sir.
I'm going to take this and rearrange it again like I did the last one. And I'm going to take the 1 over a and move it over so it's not negative. I'll take that kt and move it over there so it's not negative. And it looks like that. 1 over a, that remember that was brought over there, equals positive kt plus 1 over a0. I didn't put the little subscript t here. It means at some time t, whatever time it is. Write that down, and that part right there. So write this equation and this part in red. Highlight that part in red. Because we have the same form now. We have a y term and an x term, and that's the slope of the line, that's the y-intercept.
It's not highlighted.
So that's what a second order integrated rate law looks like. The inverse of the concentration versus time is a straight line.
Okay, so a first order and a second order are straight lines?
Well, in the first order, it was natural log of the concentration versus time is straight. In second order, is the inverse of the concentration versus time is straight.
So is it gonna look like this?
What will?
The thing, the second order plot.
If it's second order, it'll be a straight line.
Oh.
Because you have y equals some constant times x plus a constant, so
Oh.
it's going to be, it's still a linear equation.
So then we have to just plug in the a value and the k value and stuff into all these equations and see if we get a straight line.
You'll plug in the a values to that and the t. You're plotting this versus time,
Oh,
not k. K's constant.
so then when we're plotting, a is the y value, right?
1 over a is the y value.
So then we'd have to take the 1 over of all of that, and then you'd end up with like 1 over kt plus a.
1 over a is 0.
Wait, but you're taking 1 over the whole thing.
No, you just take 1 over the concentration.
Okay.
You'll see.
What if you did it like not?
What if what?
If you did it, if you didn't do a 1 over it, it would look like if you did like this concentration.
Just concentration versus time? Well, let's take a look. Can I change the slide? Going on to the next one. If it's a 0 order, remember we have 3 orders, 0, first, second. I did the first one, first order first. Now I went to the second and now 0 order. The 0 order, remember, that means that the concentration of the reactant does not affect the rate. So the rate is defined as k times a to the 0 power, which means that it does not matter what you plug in for the concentration of a, the rate's going to always be the same. And that's equal to the change in the concentration over time. So we're not going to do this one, sorry. But if we did integrate this, we would find that 0 order rate law looks like this. Concentration equals negative kt plus concentration initially. And then highlight that.
Wait, what if you graph it and it's not a straight line? Then?
One of the 3 will be a straight line. Either the concentration versus time is going to be straight, or the natural log of concentration versus time will be straight, or the inverse of time.